Alright, this video is going to very quickly go over the different types of bonds. If you need to write down notes because you missed class or whatever, then I strongly suggest you pause the video and write it down while it's on the screen and then continue it. Alright, so we've got, we're looking at types of bonding in compounds, and really we're going to look at three different types of bonding, but these two types, ionic and covalent, are kind of opposites, and so it's easier to put them in a table like this, and then after I've gone over ionic and covalent, then we'll talk about the third type. So the elements that are involved in ionic bonding is usually a metal and a nonmetal, and then for covalent it's usually a nonmetal and a nonmetal. My dog is sitting here snoring next to me, so I apologize if you can hear that in the background. How the bond is formed: an electrostatic attraction between oppositely charged ions. So you've got a cation and an anion, and they're attracted to each other because of the opposite charges. So like if you have sodium and chloride, right? Sodium is positively charged and chloride is negatively charged, and so they're attracted there, and this attraction is the ionic bond. And so that's an electrostatic attraction. It's an ionic bond because it's two ions that cause that attraction. And then in a covalent bond, two atoms share a pair or more of electrons to fill the octet rule. So the structures that we've been drawing in class look like this. And we know that carbon and hydrogen here are sharing these two electrons, and so that's a covalent bond anytime they're sharing electrons. The melting point for compounds that have ionic bonds are typically very high, and the melting point for covalent compounds or compounds with covalent bonds is usually low. Now, there are covalent networks, and those have a very, very, very high melting point, but we are not going to talk about those right now. So ionic compounds, if you dissolve them in water, they make a conductive solution, and covalent compounds do not. And the representative unit for an ionic compound is called a formula unit, and for a covalent is called a molecule. So let's talk about ionic compounds a little bit more. Why is it that chloride gets the electron and sodium gives up the electron? And a lot of students' first response is because chloride needs one electron and sodium gives one up freely. But more specifically, it's due to electronegativity. So if I go down here, right, electronegativity is an atom's ability to pull electrons closer to its nucleus. And so if an element is super, super, super electronegative and another element is not, then the really electronegative element will be able to take an electron away. So if we look at sodium and chloride closer, chloride's value for electronegativity is 3.0, and sodium's value is 0.9. And so because sodium is so much smaller than chlorine, sodium can take its electron. So sodium starts out like this with one valence electron, and chlorine has 7 valence electrons. And so because chlorine's value is so much higher than sodium, this electron comes over here. And so what you end up with is you end up with sodium plus and chloride negative. And this is due to the extreme differences in electronegativity. So you remember with electronegativity, it increases on the periodic table to the right and up, and we exclude the noble gases. Okay, and so fluorine is the most electronegative with a value of 4.0, and we'll look at the table here in a minute and what that means. But that's why ionic compounds do that, because the metals over here on this side of the periodic table have a very low electronegativity, while the nonmetals up here have a very high electronegativity. And so these nonmetals can always take the electrons from the metals, causing these to become positive and these to become negative, and so they're attracted to each other because of the opposite charges. All right, so that's an ionic bond. Now, covalent bonds are a little bit different, and so we've been looking at them, right? We have hydrogen with one valence electron and another hydrogen with another valence electron. And so these two hydrogens are going to share these electrons back and forth, and they're going to form a bond. So while these two electrons are going back and forth between these two hydrogens, neither of them are going to give it up. And so they stay close to each other so they can share those electrons. Now the same thing happens when hydrogen and chlorine get close to one another. Right? Chlorine has 7 valence electrons, so I'm going to draw 7 valence electrons around chlorine. And this electron then is going to be pulled over here towards chlorine. And so, just like in the other one, these electrons are going to be shared. Now, the only difference here is that chlorine is much more electronegative than hydrogen. Remember, chlorine has a value of 3.0, and as you'll see in just a few minutes, hydrogen's value is 2.1. And so chlorine can tug on this electron a little bit harder, and so it starts to be to where it's hanging out over here more than over here. And so that's an unequal sharing. While hydrogen in this one, in this compound, is 2.1, and this is 2.1, and so they can both tug the same amount. And so this is an equal sharing. And so the unequal sharing is called a polar covalent bond. While the equal sharing is called a nonpolar covalent bond. And so in the unequal sharing, since chlorine is more electronegative, then there's going to be a pull in that direction towards chlorine in that bond, and the electrons will be pulled closer to chlorine and leave hydrogen slightly positive. All right, so on this next slide, I've got a table of electronegativity so we can look at it right here, and you can see, oops, chlorine is over here, and it's got a value of 3.0, and hydrogen is 2.1. All right, and there's sodium with 0.9. And so you see these values for these metals, their values are relatively small, and these over here are pretty high. So when we start wanting to classify these covalent bonds as polar or nonpolar, the best way to do that, and this is really generalized, but a polar covalent bond is generally thought of as being between the electronegativity difference. So you have electronegativity difference is going to be between, so greater than or equal to 0.4 all the way up to about 1.7. And then for a nonpolar covalent bond, the value is going to be less than 0.4. And then if you want to get even more technical, you could say an ionic bond, the value is going to be greater than 1.7. So if we look at that bond with HCl, right? We said chlorine is 3.0 and hydrogen is 2.1, and so the difference in those two numbers is 0.9. And so that would fall in here, and so this we could classify it as a polar covalent. Now sometimes you have to use your your reasoning on this, if you get a value of 1.7 and you're not sure if it's polar, covalent, or ionic, you look at the atoms. And so if you have a metal and a nonmetal, then you can classify it as ionic. So let's look at a couple of examples of those. Let's see if I can just move it up just a little bit. All right, so if we're going to look at, let's say, SO2. Oops. And we want to know what kind of bond this is going to be between them, if it's going to be polar covalent or non-polar covalent, because I can already tell you it's going to be covalent because it's a nonmetal and a nonmetal. Sulfur has a value of 2.5, and oxygen has a value of 3.5. So the difference, the electronegativity difference, is going to be 1.0. And so that's definitely going to also be a polar bond. All right, but if we wanted to look at carbon and hydrogen, so these bonds in here, right, this bond, carbon is 2.5 and hydrogen is 2.1, and this is usually classified, so the difference here is 0.4, this is usually classified as nonpolar. Now sometimes this has to do also with some other things in the atoms. It's called polarizability. We're not going to get into all that. I just want you guys to get used to looking at this and thinking about how electronegativity can affect what happens in an atom. So the most important thing is to understand that when an ionic bond forms, it's because there's a large difference in electronegativity. Okay? Ionic bonds form because of a large difference in electronegativity, where the metal is just not electronegative enough to retain its electron or tug back on it. Okay, and then the last type of bond that we would need to talk about are metallic bonds. Oops. And metallic bonds are between metals. So like if you have a chunk of iron or brass, okay, which is a metal alloy, it's when metals are mixed together. There has to be some sort of bond holding those atoms together, and it's not going to be ionic because one's not going to be negative, they're all metals. And it's not going to be covalent because there's no reason for them to share their electrons, they just don't have enough to complete an octet, or their outer octet is already complete. So when you have these metallic bonds, you have to think about what's happening on an atomic level. So we have these atoms that are lined up in an organized fashion. Okay, and each one of them, we're just going to say this is iron. So each one of these is an iron atom. And iron enjoys being positively charged. So, and usually 2+ because it wants to lose the 2 electrons in the outer s orbital, the 4s. And so they give up these electrons, right? So I'm just going to draw a few. Each one would give up 2 to become 2-. So these are all just little electrons hanging out. And they're not in any kind of special order. So all these electrons are just kind of moving around in here anywhere they want to go. They're not held to any place, right? They just kind of hang out. And so we call this metallic bond, and it's when you have positively charged ions in a sea of mobile electrons. All right, and this gives metals their different and unique properties that they have. So if we take, let's say we take a mallet and we hit this, right here, it's a metal, then these can move, right? They can move because these electrons aren't sitting anywhere in particular. They're just floating around in here. Whereas if we have sodium chloride, the electron that chloride took and all the electrons chlorine has, and then also the electrons that sodium has, they can't go anywhere. They can't move. So it's not malleable. If you take a mallet and you hit a grain of salt with it, it's just going to turn into more pieces of salt. It's very brittle. And if you have a covalently bonded molecule, these electrons that are here in these bonds are stuck here. It's going to be tetrahedral shaped. While these electrons are not. And so these can move about, and that's why metals are malleable. Not only that, but if you take and you apply a current, an electric current to this, electric current is just electrons. And so then all of a sudden these electrons can move through here with the other electrons. And the electrons, instead of moving around like this, wherever they want to go, they start to move with the electric current. And that's why metals are conductive. So it allows them to be malleable and conductive, while other things are not. So that's all the types of bondings we're going to talk about right now. We will probably get into this again later on in the year and get more specific, but that's just the overview.